And this is the selectivity determining step. In this video, we're going to discuss the concept of hydrogenation. Hydrogenation is a class of reactions that involve adding H2 across a pi bond. Here, we're going to talk about adding H2 across a carbon-carbon pi bond, reducing that pi bond in a hydrogenation reaction. If we look at this example hydrogenation reaction, this looks like it might not be a bad reaction. We've seen lots of alkene addition reactions that look a lot like this. In fact, this reaction has a very large negative delta H. It is a very thermodynamically favorable reaction. However, this particular reaction as drawn rarely happens, if ever. And the reason is it has a very large activation energy. Why does it have a very large activation energy barrier? There's two real reasons. One, when we think about our typical alkene addition reactions, our alkene reacts as a nucleophile and reacts with a fairly strong acid. H2 is a very weak acid. It has a pKa of around 35 or so. It's a very weak acid, and it's not electrophilic enough to be attacked by a neutral pi bond. The second reason is that if we think back to our typical alkene addition reactions, when the alkene would attack H2, it would have to kick out H- as a leaving group, and H- is a really bad leaving group. So for both of these reasons, the hydrogenation as written does not occur. We'll need to add a catalyst to this reaction in order to make this reaction occur. There are several hydrogenation reactions we're going to look at, and this can best be organized in a table format. So let's draw a table to organize our hydrogenation reactions. We'll have the starting materials here on the left, our reagents along the top, and the products of the hydrogenations in the middle of our table. We can think about different kinds of starting materials. We can think about an alkyne starting material, an alkene starting material, an alkane starting material, or even in certain circumstances, a benzene ring as a starting material. Now, before we even get started, let me talk a little bit about benzene. Benzene is a highly conjugated molecule that has a special classification we call aromatic. It is an aromatic molecule. I'm not going to get into what that means here, except to say that an aromatic ring is exceptionally stable. The pi bonds are not very good nucleophiles to begin with, and an aromatic ring is an even worse nucleophile than a typical pi bond. So we'll just throw that out there for now, and we'll talk about the implications of that as we go through this list. Our first set of reaction conditions we're going to learn is hydrogen gas with a catalyst that we write on paper as PD/C. When we say it out loud, we say this as palladium on carbon. So let's talk about what this means. We'll talk about how the reaction works, and then we'll fill in what the products of these are for these various starting materials. So let's take a little bit of notes about these reagents. We'll start with hydrogen gas. Hydrogen gas, the way this typically works is you would fill up a balloon with hydrogen and you'd attach it to the end of a syringe with a needle on the end, and you'd put that into your reaction, and that way you could have a hydrogen atmosphere in your reaction, and that hydrogen would diffuse into your solvent so you can do the reaction. Hydrogen gas, when it reacts in these types of hydrogenation reactions, is stereoselectively syn. That means that when the hydrogens add across the pi bond, they will stereoselectively add to the same face of the pi bond in a stereoselectively syn manner. The palladium catalyst that we're going to use is the strongest of the reductants that we're going to see today. We're going to see a couple of different reaction conditions that we're going to talk about, and the palladium is the strongest reductant. It will completely reduce all of the pi bonds as far as they can be reduced in that particular reaction. So let's talk a little bit about how this reaction works. Let's talk a little bit more about palladium. Palladium is a precious metal. It's an expensive metal, and you really don't need very much of it in order to do these reactions. It's a really pretty good catalyst for what it does. The problem is that it would be hard to store a big chunk of palladium and then just flake off just a tiny, tiny amount that would be hard to measure, and then you'd have to put it in your reaction. It's actually kind of cumbersome to deal with. So what we do, and the reason that we write the catalyst this way, is we take palladium dust and we sprinkle it onto little tiny pieces of carbon so that the bulk of the material is really this carbon support, and it's supporting these tiny amounts of palladium on that carbon. So we call it palladium on carbon is the catalyst. That means you can store it better, you can measure it out better, and when you measure it out, most of the mass you're measuring out is the carbon, and so again, you really only need a tiny amount of palladium to do these reactions. That's why we indicate the catalyst this way as palladium on carbon. But when it does react, it is a surface level reaction, so it reacts on the surface of the palladium. So you can imagine a palladium surface for this catalyst. You have your hydrogen gas, and you have some kind of alkene as your starting material. So we're going to indicate the mechanism of this reaction across the palladium surface. We'll call it a mechanism. Probably doesn't really so much happen this way. When you get into these metal-based systems, our traditional arrow pushing doesn't quite have the same effect as it does for a traditional organic chemistry reaction, but we'll go through it here all the same. So the first thing that happens is the hydrogen gets absorbed onto the palladium, breaking the hydrogen bond and forming bonds to palladium, as well as the alkene gets absorbed onto the palladium. So the alkene pi bond breaks and the alkene gets absorbed on the palladium. Let's draw in the hydrogens already on the alkenes. We can see them here as well. When this happens, this allows the alkene and the hydrogen to get close enough to each other to react that the hydrogen can react with one of the carbons, and we can add the hydrogen to one of the carbons of the starting material. We still have one bond to palladium, one hydrogen is attached, and we still have one more hydrogen attached to the palladium surface. We can then finish this reaction out by adding that other hydrogen to the starting material, and we end up with our product. Again, notice that the hydrogens that were added, it would be this one here and this one here, were added stereoselectively syn to the same face of the former alkene. So this is how this reaction occurs. So if we start with an alkene, we will reduce this alkene to an alkane. We'll add hydrogen across the pi bond to reduce the alkene to an alkane. If we start with an alkyne as our starting material, we'll end up going through the same process. And again, because this is stereoselectively syn, we'll end up with a stereoselectively syn addition, and we'll end up with a cis alkene. Now, what's interesting about alkenes, we just talked about, they are also reactive with this very strong reductant. So as soon as this alkene forms, it goes back and it does another cycle through this process. And so the net effect with our strongest reductant is that when we start with an alkyne with 2 pi bonds, we get a complete reduction to the alkane. It gets first reduced to an alkene in one step, and then in a second step, it gets reduced to the alkane. We end up with 2 hydrogenation reactions, 2 additions of hydrogen across both pi bonds, and we completely reduce the alkyne to the alkane. When we start with an alkane, there are no pi bonds. This mechanism can't occur because there are no pi bonds, and so we end up with no reaction here for the alkane starting material. And the same is true for the benzene ring. We talked earlier that the benzene ring, because it is aromatic, it is exceptionally stable, and because it's exceptionally stable, it will not react under these reaction conditions. So this is one set of reaction conditions. The strongest reductant will completely reduce our pi bonds to alkanes. But when I look at this results as a researcher, as a scientist, this gives me an idea for a research question. If the alkyne reacts to give a cis alkene, and then that cis alkene immediately reacts again, is there some way to stop the reduction after that first reaction? Stop it at the alkene stage? And the answer is, of course, yes, there is. We have already thought about this, but we can't use the palladium on carbon catalyst because it's the strongest reductant. It's so strong that it will reduce the alkyne to an alkene and then immediately the alkene to an alkane. So I need some kind of weaker reductant that can reduce the alkyne to the alkene, but then is too weak of a reductant to reduce that alkene to an alkane. And so the way we do that is, again, with hydrogen gas and a catalyst we call Lindlar's catalyst. Lindlar's catalyst is a lead poisoned catalyst. It's still palladium based, so it's our regular palladium catalyst, but it has some lead doped into it, and that lead reduces the reducing ability of the palladium, making it a weaker catalyst. It's a lead poison catalyst, it's a weaker catalyst. It can reduce an alkyne to an alkene, but it is not strong enough, it's weakened, it's poisoned, it's not strong enough to reduce the alkene to an alkane. So we can solve this problem by using a poisoned catalyst that's weaker, and instead of reducing an alkyne to an alkane, it reduces an alkyne to a cis alkene. It is still palladium based, so it is still stereoselectively syn, and so we reduce an alkyne to a cis alkene. When we start with an alkene starting material and we react with H2 and Lindlar, we just talked about how the fact that it's a poison catalyst makes it a weaker reductant, and it is not able to reduce the alkene. So if we start with an alkene, it's still not able to reduce the alkene, and we have no reaction for Lindlar's catalyst with an alkene starting material. Again, the alkane has no pi bonds to begin with. The benzene ring was not reactive enough to react with our strongest catalyst, so it's certainly not going to be reactive enough to react with a poison catalyst, and so we get no reaction here as well. When I look at this result, though, this also gives me an interesting opportunity for research. If I can reduce the alkyne to a cis alkene, is there a way I could reduce it to a trans alkene? I mean, the cis alkene is nice, but what if I want a trans alkene? And the answer is yes, of course, we can do that too. We're going to need a completely different system, though. We're going to use a different set of reagents. We're going to use sodium metal and ammonia as our solvent. Sodium metal and ammonia as the solvent is our third set of reaction conditions. Let's talk about how that works. This is going to go through a completely different mechanism entirely. We're going to start with an alkyne, and we will react it with sodium metal. Sodium metal has 1 electron in its valence shell, and so it's going to use that 1 electron. It's going to add that 1 electron to the pi bond of the alkyne. When it does that, that builds up too much electron density around this carbon, so we're going to break the pi bond and put 2 electrons, take both of those electrons and push them onto the other carbon of the former alkyne. That's going to form a radical on one carbon and a lone pair anion on the other carbon. These 2 carbons now have different hybridizations. The carbon with the lone pair is now sp2 hybridized, so it's trigonoplanar. The carbon with the radical is still sp hybridized and still linear. What's interesting, though, is that this carbon with the lone pair and the alkyne is now a very strong base. So we have our ammonia solvent. The alkyne strong base can take a proton from the ammonia solvent in an acid-base reaction, favoring the product. products. pKa of ammonia is about 33, 35, and the pKa of an alkene is about 45. So the weaker acid will win and will form an alkene carbon-hydrogen bond. And we still have our radical carbon on the sp2 hybridized carbon. And so the way that this reaction is going to finish up and how we're going to get the trans-alkene is we're actually going to do these same two steps again. We're going to take another equivalent of sodium metal with its one electron. We're going to take that one electron and add it to the existing one electron on this carbon. That's going to add a lone pair of electrons to that carbon and a negative charge. And this is the selectivity determining step. When we do that, we can have the lone pair and the negative charge on the same side as the hydrogen, or we can have it on the same side as the methyl group. It's not so much the lone pair that's interesting, is this other methyl group, though, that's interesting. If the lone pair is on the same side as the hydrogen, that means these two methyl groups, these two largest groups, will have to be on the same face as each other, and that's sterically bulky, that's sterically clashing. So instead, we're going to have the lone pair and the negative charge on the same side as the methyl group, so that those two methyl groups can be as far apart from each other as possible. That minimizes the strain in this molecule and gives us our trans selectivity. Again, here we have an anion, so we can do an acid-base reaction with ammonia, and this will form our product of the trans alkene. And so we get a trans alkene when we react an alkyne with sodium metal in ammonia as a salt. This system is not a strong enough system to reduce an alkene, so if we start with an alkene, we stay with an alkene. With an alkane, we, again, don't have any pi bonds to reduce anyway. This time, however, with the benzene ring, we actually do get a reaction. The reaction with the benzene ring is to turn the benzene ring into a 1,4-cyclohexadiene. So let's talk a little bit about how that happens. We take our benzene ring and we react it with the sodium metal. The sodium metal will add one electron to one of the carbons of the benzene ring. And then to get those electron domains as far apart from each as possible, we're going to break the pi bond, and we're actually going to move these electrons all the way down to the carbon opposite where we're going to put this radical electron. So the radical will be at one carbon, and the lone pair negative charge will be at the opposite position across the benzene ring. That gives us our anion that we can react with ammonia in an acid-base step, favoring the product. And we still have one radical left, and so we'll do this again. We'll react with another sodium metal to put one more electron on that carbon. It gives us another anion that we can react with another equivalent of ammonia in an acid-base reaction, favoring the product to form the 1,4-cyclohexadiene product. This is an overview of the various hydrogenation reactions we can do. By knowing what starting material we're starting with, and by choosing our reagents carefully, we can form a variety of different products with our choice of how we want the selectivity to occur. Do we want a complete reduction? Do we want a cis or a trans alkene? Do we want to reduce the benzene ring or not? We have control now by choosing our reagents carefully.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.